So if you're trying to generate a super electrophile here with an alkyl halide, so an alkyl halide and iron chloride, what's going to happen? What's going to happen is that the lone pairs on the chlorine, I'm going to add there first. So now the iron has a negative charge, the chlorine has a plus charge. But then what happens is you generate a carbocation. Now we got to be careful with carbocations, of course, because if you make a carbocation, carbocations can still rearrange. So what kind of carbocation is this? This is a secondary carbocation. So we want to look for the sigma bonds 2 bonds away. And if you look, there's a sigma bond 2 bonds away, where if we did a rearrangement, we get a tertiary carbocation. And that's actually the super electrophile species that's going to react. Okay, so comparing and contrasting Friedel, this idea of acylation, adding the carbonyl group, versus alkylation, just adding a carbon group. The difference is, with acylation, obviously you're adding a carbonyl. There's no rearrangements. For alkylation, there can be rearrangements. So first I'll draw out the possible products. Okay, so I drew out a lot here. So let's kind of go through it step by step. So in each case, one way these can react, right? A mechanism is just showing a possibility how things react. But you can have the lone pair on chlorine in each case go for the iron. So that gets you to something that looks like this. Iron with a negative charge and the chlorine with a plus charge. In this case, you can have the lone pairs come down and have the chlorine leave, or just have the chlorine leave. And you end up with something like this. This cannot undergo rearrangement. So this will not do rearrangements, right? However, this is a more traditional carbocation. The chlorine breaks off. Now we have like a carbocation that we're kind of used to, right? Whereas this doesn't lead us to a normal carbocation, but this this different thing, this oxocarbenium, will actually lead to not have carbocation rearrangements, whereas these will. So that's the major difference, is the acylations, when you're doing these things with the carbonyls, they won't rearrange. The things with the alkyls will. Okay, so I'm just going to focus on, remember, two parts to this. So you should be able to look at something like this and know what's going to be added and where it's going to be added without doing really much of anything. You should be able to recognize that this sulfur is going to be an electron donating group because it has lone pairs, right? That's going to donate electrons to the ring. That's going to direct ortho and para. You should recognize that the Br2 in this are going to give you a bromine, and that's what's going to add in. And so I gave the product as para, as ortho. Sure. So if I wanted to ask for sigma complexes for this, and just maybe what's going to happen, I could draw out the super electrophile generation. So the bromine's going to react there, and we're going to get this one bromine with a plus charge, this iron with a negative charge. The pi bond is going to react. The reason I chose this pi bond is because I told you the product needed to go here. So that's the pi bond to work with. Now that's going to be the first step, and that first step we always call that the addition step. And after the addition step is when we actually create the so-called sigma complexes. All right, so we have the bromine here. This is the part that lost it. All right, sigma complexes again are just resonance forms of the starting material resonance forms of the intermediate after the addition step. So we can start drawing some resonance structures here. All right, and so these are just sigma complexes. All right. So after the addition step, you can draw another one. Resonance arrow. So So there's always 3 sigma complexes, but if you have an electron donating group with lone pairs, you're going to have 4 sigma complexes. So if I label these A, B, C, and D, the best one of these is D because all the atoms have full octets. Right? Now this doesn't actually finish the reaction. This is like kind of analyzing the sigma complexes. So if I ask you to do this is great, right? But then what I would do is okay, but that doesn't get me to this, which I need to get to, right? So what I would do is I would redraw that first sigma complex, the first thing you did. There's the bromine, there's the plus charge, there's an H, there's this bromine, Fe, Br3 minus. So now to do this elimination step, I redrew the first sigma complex, doesn't matter which one you do it, sometimes this is easier. Electrons there, take that H, and that gets you that elimination. Again, things to remember, it's electrophilic aromatic substitution. What you're always substituting is an H off the ring, right? So be careful what H you end up taking from the ring in this final elimination step.